In this video, we're going to talk about how we can construct a field from an integral domain. It's called the field of quotients. And before we get into a formal definition, let's just talk about the motivating idea. So once upon a time, all we had was the integers. So the set of all whole numbers and their opposites. So 0, plus or minus 1, plus or minus 2, and so on. And that in itself forms a perfectly nice self-contained number system with operations of addition and multiplication. But at some point we wrote down some equation that's expressible in integers like 3x plus 5 equals, 19. And we said we'd like to be able to solve this. It's a linear equation, so we'd like for it to have a solution. But then we ended up with 3x equals 14, 14, and got x equals, well, there is no integer that multiplied by 3 gives us 14. So we needed to expand this number system so that equations like 3x plus 5 equals 19 or 3x equals 14 would have a solution. So how did we do this? Well, the way that we approached this was we just invented a number. X equals 14 over 3, or it could be thought of as 14 times a multiplicative inverse of 3. That is, we just attached multiplicative inverses of all of these integers to our number system in a way that's coherent, leads to well-defined operations, and doesn't force us to divide by 0. Okay, so that's going to be the motivation for what we do, is we're just going to say, what if we just attached multiplicative inverses? And the way that we're going to do that is we're not just going to attach multiplicative inverses, we're going to attach quotients of ring elements. So that not only do we have a multiplicative inverse of 3, but we have a ring element called 14 over 3. Okay, so that's where we're going to start, except we're not going to start with the integers. We're going to start with an arbitrary integral domain D. So here's our definition. So let D be an integral domain. I'm just going to call that ID. D be an integral domain, so commutative with unity and no zero divisors. Okay, we define the field of quotients of D as follows. And this definition is going to be a little bit complicated because there's a couple of steps to it. So first we're going to define S to be the set of all ordered pairs AB, where A and B both belong to the integral domain, and B is non-zero. Okay, why is B non-zero? Because we're going to think of the ordered pair AB as being a formal representation of what we'll think of as the fraction A over B. Even though A and B may not be integers, they may be just elements of some integral domain. For example, A and B could be polynomials, and that'd be fine, as long as they're polynomials over an integral domain. Okay, so A comma B is going to represent the fraction A over B. But then if we stop there and just say, let our field consist of all of these ordered pairs, we're going to have a little bit of a problem, because if we want to think of this A comma B as being like a fraction here, well, we know from middle and high school mathematics that different fractions can represent the same number, or can represent the same element of a number system. For example, we know that 3/4 is equivalent to 6/8, and we don't want to think of those as two separate elements. We want to think of those as the same element. So we're going to need to define an equivalence relation that will treat 3, 4 as the same element as 6, 8. So we're going to cluster these together. So we're going to define an equivalence relation on S. And I'm going to call it tilde. And the way we're going to define that is A1, B1 is equivalent to A2, B2 if and only if. And you may think, well, we're going to define A1, B1 to be equivalent to A2, B2 if and only if A1 over B1 equals A2 over B2. But what does that mean exactly if what we're dealing with is an abstract integral domain? It's not clear. We don't have any well-defined construction of fractions yet from which we can make that inference. So we need to have some other way of stating what it means for these to be equivalent, only in terms of the operations on the integral domain. So here's how we do it. One thing that we know from middle school math is that for these two fractions to be equivalent, one way to check that they're equivalent is to cross multiply. That is, check that 3 times 8 equals 4 times 6. That's going to be exactly what we do here. We're going to define these to be equivalent if and only if a1, b2 is equal to a2, b1. And then that's a statement that makes sense in our integral domain. So that's what it means for two ordered pairs to be equivalent. And then we define f as follows. So f is equal to s modulo the equivalence. In other words, the set of all equivalence classes of S. So for example, if D is just the integral domain of the integers, then one element of F is the equivalence class of 3, 4. And that equivalence class consists of all ordered pairs that are demonstrably equivalent to 3, 4. So 3, 4, 6, 8, 9, 12, and so on. It's even going to have some ordered pairs consisting of negative integers like -3, -4. That would also be perfectly fine. Okay, so the equivalence class of 3, 4 consists of all of these different ordered pairs which represent fractions that reduce to 3/4. That is one element of F. All right. So that's our set-wise definition of this field, but for it to be a field, we need operations. So we need to define how to add and multiply elements of F. So the operations are for all elements of F, so the class of A1, B1, and the class of A2, B2, for all of these in F, we define, first of all, how do we add two elements of F? Well, there's a way that we can sort of logically figure out how we might want to define this, because we want A1, B1, or that equivalence class to represent the fraction A1, B1, and A2, B2 should represent the fraction A2 over B2. And, how do we normally add fractions? Well, the first thing we do is we say we'd really like to have a common denominator. And because we're dealing with equivalence classes, we can create a common denominator. We can say A1, B2 over B1, B2 is equivalent to A1 over B1. All right, and the reason that that's true is because we can actually check using cross multiplication that these are equivalent. If we cross multiply, we get A1, B1, B2 on the one hand, and then on the other hand, we get A1, B2, B1. And because we're in an integral domain, multiplication is commutative, those come out the same. Similarly, A2 over B2 is equivalent to A2, B1 over B1, B2. And then when we add those together, we just get A1, B2, because we're now adding things with the same denominator, A2, B1 over B1, B2. And then that's the sum. That's the sum of these two fractions. So we're going to define the sum of these equivalence classes to be the equivalence class of A1, B2 plus A2, B1, comma, B1, B2. Now there's a whole issue of well-definedness here. I mean, how do we know that if we add different representatives of the same equivalence classes, we get essentially the same answer up to equivalence? We're going to need to check that. Okay, but first let's define multiplication. This one is always a little bit more straightforward to define because, well, multiplication of fractions, once you understand how it works, it's easy to do. We just multiply numerators and multiply denominators. So that's our definition. This whole thing here is the definition of something that I claim is going to be a field, but it takes some proving. And I'm not going to prove all of the properties of a field here. This video is already getting too long. I just want to show how we might prove that the operations are well defined. And I think I'll do it for addition and then leave multiplication as an exercise. So let's zoom this out so we have the definition in frame here. But let's prove, there we go. Let's prove that addition is well defined. So here's the proof that addition in F is well defined. Well, let's suppose that we have two equivalence classes that are the same, A1, B1, and A1 prime, B1 prime. So really, these aren't so much two equivalence classes that are the same, it's really one equivalence class represented in two different ways. And let's suppose we have this other equivalence class represented in two different ways. So A2, B2 versus A2 prime, B2 prime. And I apologize in advance for the notation being kind of ridiculous here. But I wanted to keep things as consistent with the definition as possible. The definition's got A1, B1, A2, B2. All right, so what we want to show is that adding up these two equivalence classes, A1, B1, and A2, B2, yields the same answer as if I added their other representatives, A1 prime, B1 prime, plus A2 prime, B2 prime. That's the goal. I want to show that these yield the same result. All right. Well, let's just start operating and see what we get. We know that the sum of A1, B1 and A2, B2, that's equal to the class of A1, B2 plus A2, B1. Oops, there we go. And then B1, B2. That's the sum of these two classes this way. Now the sum of these two classes this way is going to be A1 prime, B1 prime, plus A2 prime, B2 prime. And that gives us A1 prime, B2 prime, plus A2 prime, B1 prime, B1 prime, B2 prime. There we go. There's a lot of apostrophes there. And we need to verify that these two equivalence classes are the same. And the way that we're going to do that is we're going to show that these two ordered pairs are equivalent under our equivalence relation here. By the way, I don't think we ever showed formally that this is an equivalence relation. That again would be a good exercise to work out, is prove that that relation is reflexive, symmetric, and transitive. We're skipping over that right now. Okay, but to show these are the same, well, let's just do cross multiplication and see what we get. So to show this, we cross multiply. And I'll put that in quotation marks there. All right, so we get A1, B2 plus A2, B1, all of that times B1 prime, B2 prime. And I'm going to put the rare equal sign with a question mark over it just to say I am multiplying these two different pairs of elements and hoping I get the same thing. I'm not claiming outright they're the same thing. Multiplying that by B1, B2. Okay, so again, I'm just doing this little game here where I multiply these and multiply these and hope I get the same thing. All right, so if I multiply all of this out, what I'm hoping for is that A1, B2, B1 prime, B2 prime, plus A2, B1, B1 prime, B2 prime, wow, that's a mouthful there, is equal to, and again, I'm not sure that this is true yet, A1 prime, B2 prime, B1, B2, plus A2 prime, B1 prime, B1, B2. Okay, so now let's just step back here and take stock of what we've got. The obstacle I'm facing here that I'm noticing is that here I have like A primes, A1 prime and A2 prime, and I would very much like not to have them. All right, so let's just think, how might I get rid of those? Well, remember that one thing I haven't used that yet is the fact that this equivalence class is equal to this equivalence class. These ordered pairs are equivalent. All right, so I have some knowledge here that I haven't used yet. All right, so let's just write this down. We know since A1, B1 is equivalent to A1 prime, B1 prime, that was a part of our assumption of what we were doing. We know that A1, B1 prime equals A1 prime, B1. And we also know since A2, B2 is equivalent to A2 prime, B2 prime, that tells us that A2, B2 prime is equal to A2 prime, B2. Okay, great. So how are we going to use that? Well, over here on the left, we have A1, B1 prime, and over on the right, we have a term that has A1 prime, B1, and then the rest of it is, what do we got? We got, switch colors here, B2, B2 prime, and we got B2, B2 prime over here. So I think these terms are equivalent. And then what about the next term? We have, let me see if I can switch colors here. I'll use red for this part. So we've got A2, B2 prime, or do I? Brief moment of panic here. You know, I think that I forgot to make this a B2 prime when I multiplied by B2 prime here. So let's just fix that. Okay, that was just a error on my part, keeping track of the apostrophes. So I've got A2, B2 prime here, and I've got A1, different color, or B1, B1 prime the rest of the way. Okay, and then over here I've got A2 prime, B2. Okay, so again, A2, B2 prime is equal to A2 prime, B2, and then the rest is B1, B1 prime. So I think these two terms are known to be equal. Okay, and I'm not going to write that whole thing again. I'm just going to say, because of these equivalences, the above expressions are equal. And that's excellent. Okay, because now we know that the sum of these two equivalence classes ended up being equivalent to the sum of these two classes. Okay, so I'm just going to move over here to the left to finish this up. So A1, B1 plus A2, B2, the sum of those equivalence classes is equivalent to, in fact, it's the same class as A1 prime, B1 prime plus A2 prime, B2 prime. Okay, so that proof has the personality of a paper towel, but it does prove that addition is well defined. Addition of classes in F is well defined, which means we have a well-defined addition operation. You can also prove multiplication is well-defined. It follows sort of the same structure where we say, well, suppose I've got the same two classes expressed each in two different ways. So I start with this setup here. Oops. I start with this setup. And then instead of adding, I multiply. And I show that the multiplication gives me the same result each time. And again, it's a matter of using these two facts here. Need to use these. And by the way, if you were writing this proof a little bit more formally and not using a multicolor palette, you would probably start by stating these two facts here, and then start by calculating these two, and then start with this expression, distribute it out, and then replace the appropriate things here with what we know is equivalent, and work your way towards this expression here, which can then be factored to give this expression here. So you'd write it in a little bit more linear fashion. Okay, so anyway, that is a proof that what we have is a set with well-defined addition and multiplication. Does not prove it's a ring, does not prove it's a field. We will work on that in the next video, or at least parts of it.